That's recording now. So as I was saying, there's one topic that I like to talk about before final projects, and that's this idea of gear ratios. And the reason for that, now I think we're going to do, for us this semester, I think we're going to do a probably a drone-based final project. We'll talk about why that is here in a second. But historically, we have done final projects where I give groups a motor and ask them to construct some kind of device that uses that motor to accomplish some task. And what I would get is students would tell me, well, during the presentations, the students would say, well, the motor didn't have enough power, or we couldn't get enough torque out of the motor, or something. They would say things, and I came to the realization of, well, nobody's ever talked to them about how do you adjust or modify or change the torque output, or how do you change the output of a motor or an engine. We've talked about motors and engines. We've not talked about transmissions, and I don't expect you guys have, some of you have some knowledge of transmissions, and that's fine. We're not going to build a automatic 10-speed transmission or anything like that, okay? But that doesn't mean we can't talk about some of the basic principles associated with them. And so I found that after I built in this lecture in the intro class, the quality of the final projects improved great's in the semesters moving forward after that. So it's whether we actually do those kind of final projects in here or not, I find it's a good little lecture when we've got an extra day, and today we have an extra day to talk about what we call gearing ratios. And really what that translates into is if I've got a motor or an engine, and we talked about those before, how do I change or modify, or what can I do to the output of that motor or engine, okay? We talked about generating electricity, and we talked about transmission of electricity, and we talked about AC versus DC, okay? And to get AC electricity that comes out of our wall, that electricity needs to go back and forth 60 times every second, meaning my generator needs to be turning at roughly 60 times per second, or structured in such a way it generates 60 hertz electricity. So how do I get that exact speed? Well, if my turbine in my power plant spins at a different speed, can I use it? Well, yes. I just have to hook up a certain set of gearing ratios, a transmission that adjusts the speed of the output to turn the generator at the right speed, so I get 60 hertz coming out of the wall. Okay, so I guess what I'm saying is there's all kinds of applications for what we're going to talk about. We're going to talk about some of the it's the base knowledge. We're going to talk about a little bit of physics today. We're going to do a little bit of algebra, nothing complicated, and nothing, those of you who are taking calculus and physics now, it's not as in-depth as what you've done there, but we do need to lay down some base knowledge, okay? So first and foremost, this concept of torque. You've probably heard that term before. Maybe nobody's talked to you about what it is, right? Kind of like the difference between a motor and an engine. Maybe nobody's really formally talked to you about that. Let's talk about torque. Sometimes we refer to torque as what's called a moment, but that's really kind of more for engineers a lot of times. Let's refer to it as torque here. Okay, torque refers to the tendency of an object to rotate. Okay, it is mathematically it's what happens when you take a force and the lever arm and multiply them together. Now, what does that mean? Let's say that I've got a wrench here, and I need to spin this nut, and this nut's on a threaded rod or a bolt coming in and out. And I need to spin this, get this thing to rotate. I want to rotate. We said torque is the tendency to rotate about a point. I want this thing to rotate about this point. Okay. All right. If I'm applying a force, do I push this way? No, that's not going to do me any good, right? Okay, let me grab my eraser. Because I don't have an eraser, I gotta grab the rag. That doesn't help. So the direction of that force is important. Now we're not gonna get too far into vectors, and let's not talk about vectors today, okay? If it was a physics class, we'd have already talked about vectors, we could talk about that. Let's just understand the direction of the force is important, okay? Now, do I grab on here? So I can't push this way, right? So let's say I apply a force here. Can I grab on right here and do that?
You can, but it won't work as well.
I know, I can, but it's not as good, right? It's not as good. So, probably want to grab out here, all right? Put my force there, okay? So the force times what we call the lever arm. The torque is going to be force times lever arm. I'm using you could just use a capital T here. I'm using a capital tau. That's a Greek letter. That's kind of how I draw a tau. People on the internet are going to tell me that's not how you draw a tau. That's okay. I've learned over the years. That's how when I'm talking about torque, that's the letter I will use for it, right? So torque is, again, the product of force times lever arm. So if this thing is not spinning, if it's rusted up, how do I get it to spin? Well, I can apply more force, right? Put both hands on here. Maybe hang off of it if I can, right? Somehow I can increase the force applied out here, okay? What else can I do? Well, you can. You guys ever heard of the term cheater bar? Probably heard that term before. What is a cheater bar?
It's like a long piece of pipe that goes on the outside of it so you get more leverage.
Exactly. You put a pipe, all right? So a cheater bar is where you take a pipe or something like that, right? When I change my own oil, I've got a couple of pipes that'll fit inside each other. And I'm off the screen over here, okay? But I can come out here as long as that pipe is, and what I can do is I can increase the lever arm, I can apply the same force out here, I can increase the lever arm, and that increases the torque. So I can increase either one of those, as long as I don't break something. I mean, I will reach a point where I'm applying too much torque and something's going to break off, okay? And that's another set of problems. But again, torque is the product of force and the length of your lever arm. How far away from the point of rotation are you applying that force? To get the most torque, again, the direction's important. We're not going to talk about vectors here, but I can just tell you to simplify it. To get the most torque, if the force and the lever arm are perpendicular to each other, you'll get the most torque. Okay? If you've had some calculus or talked about vectors, it's actually the force vector you take the cross product of the force vector and the vector of the lever arm. And again, if that means anything to you, you understand that if they're perpendicular, that's where you get the most value. Okay. All right. Questions there so far? Okay, so we have to understand torque first. There's two quantities that are important here. Torque is one. Rotational speed is the other. Rotational speed, which we'll call omega. Right? I use lowercase omega, Greek omega there. That's how I draw it. It's kind of like a W with a loop in it. Omega, the rotational speed, is just simply the speed at which the object's rotating. Okay? In your car, you've got what we call the tachometer. The tachometer is what's measuring the speed at which your engine's rotating. Okay? And it's measuring, and the numbers that are displayed there, and there's always some symbol on there. It's either multiplied by 100 or 1,000, depending on your tachometer. Almost all of them are by 1,000. Okay? And so what that's telling you is it's telling you the speed at which your engine is rotating and driving the transmission. Okay? But it's just simply the rate. Right? So it's the dimensions. If I could spell, that would help. Dimensions is time to the -1 power, or per time. That's the dimensions of rotation speed. And it's technically rotations. It's arguable as to whether rotation is a dimension or not. I mean, I would say it is. Science typically says it's not, but it's basically per time, or rotations per time is the dimensions there. So the units are per minute in the case of rotations per minute, or per second. Right? If I've got what we call per second, if I take second to the -1, that's what's called a hertz per second. That's a hertz. So the electricity coming out of our wall is at 60 hertz. It's oscillating every 60 seconds, or 60 times every second. Okay, so it's 60 hertz is 60 per second. Okay. All right. So two quantities there. I guess 4. When you think about torque, is force times distance, and then omega, or the rotational speed. So there's 4 quantities there. Okay. So again, historically, if I do final projects where you've got to take a motor and do something with it, how do we get more out of it? Well, we've got to understand these 2 quantities and how they're related, torque and rotation speed. Okay, now, so let's say I've got 2 objects that rotate together. Anybody hear of Isaac Newton? Yeah, kind of important guy. Physics, a lot of times your Physics 1 class is going to be the initial, kind of the first half of Physics 1 class. A lot of times it's the study of Newton's 3 laws, first 3 laws of motion. Okay. The third law, Newton's third law, is the action-reaction law. For every action, there's an equal and opposite reaction. Okay. So what happens is, if, let's say this is gear A, let's say gear A is rotating at omega A. Gear B, so if this one's rotating like this one's going to rotate like this. They're going to rotate in the opposite directions when I've got gears. When they mesh together, if gear A is rotating clockwise, gear B is going to rotate counterclockwise. Now, again, rotate this, because I find myself standing over off the screen quite a bit. So Newton's third law says that for this thing to rotate, when the gear teeth hit each other, okay, there's a force applied out here by the tooth on gear A. Okay? So that's applying a force to the tooth on gear B, and that's causing the gear B to rotate. Because I've got a distance out here, so I'm causing torque on gear B, causing it to rotate. All right. Newton's third law says if those 2 teeth basically don't fuse into one another, or they don't pass through each other, for that means the only other alternative is that gear B is applying a force back on gear A. They're pushing against each other. Otherwise, the 2 surfaces pass through each other. All right, I can push on the air. The air applies a little force back on me, but not as much as I'm applying on it. Well, it is, but anyway. But I can, again, when I've got 2 surfaces that don't pass through each other, they're applying equal and opposite forces to each other. Okay? So, if that's the case, let's talk about the torque. Again, remember the torque, which is force times a lever arm. Well, what is my lever arm? Well, if gear A is rotating about point A there, and I've got a radius for gear A, that's my lever arm. So it's rotating about this point, and the force applied is out here, this distance RA. And then for gear B, the lever arm is RB, the radius of gear B. Okay? So that means that the torque that, let's say I've got a motor hooked up to gear A. So that motor is going to apply a torque to gear A. And that torque is the force out there at the edge of the teeth on gear A multiplied by the radius of gear A. That's the torque. So again, motor and engine applying to gear A causes this force out here at distance RA. And then the torque that gets applied to gear B is equal to the force B times the radius of B. And those forces are equal. All right, so if I solve these, force A is equal to what? I've got torque A over RA. And if I solve this one for force, the force B is equal to torque B divided by RB. Our good friend Isaac Newton says those forces are equal and opposite because for every action there's an equal and opposite reaction. So Newton says those forces are the same. Force A is equal to force B, or force B is equal to force A, meaning the torque at A divided by RA is equal to the torque on gear B divided by the radius of B. Okay, I'm going to write that over to the side. That's important. Torque A over RA is equal to torque B over RB. And we're going to come back to that. So actually, I think we'll work. I've designed this presentation for a smart board or interactive whiteboard, but I think this is actually going to work better because those are going to stay there. Because I think, yes, so let's talk about rotation speed. So we said there's two factors, right? There's torque and rotation speed, omega. Okay? So we talk about the rotation speed. When two objects rotate together, the speed out at the tip, the teeth, the speed of the teeth of these gears are going to rotate the same. And if I've got a pulley with a belt hooking up two discs and a pulley spinning both of them, same thing, right? Because the speed of the pulley, any point on the pulley is going to be the same, and we'll draw that in a second. Right? We'll draw that one in a second. We can talk about pulleys in a second. Let's talk about gears first. So understand that as this one's spinning, right? Again, this gear is not going to pass through, or this tooth is not going to pass through this tooth. They have to be moving at the same speed. So the speed out there at the edge is going to be the same. Now, so what we're saying there is I'm going to erase the forces here. So what we're saying here is that the speed, I'm going to call it V because in physics we use velocity and speed is the measurement of velocity. Okay. Again, if you've talked about vectors, speed is the magnitude of velocity. And so we're saying if this tooth on gear A is moving at speed VA, then the tooth on gear B is moving at the same speed. We'll just say VB. And here we're saying that VA is equal to VB. Okay? They have to move at the same speed because they're not passing through each other. Now, if that's true, now how do we find VA? Well, the speed of point A is going to be, speed, of course, is distance per time. Okay, that's speed. Speed's distance per time. Makes sense. Well, remember, per time is omega. Omega is per time. It's measurement per time. So the speed at point A, so the distance traveled by this guy, circumference of that circle, 2 pi RA times omega A. Okay? So that's the speed of the tooth out here on gear A. The faster omega A is, the faster the speed of the tip is. We can do the same thing with VB. VB is going to be 2 pi RB omega B. Excuse me. Okay. And again, because they're not passing through each other, it's the same speed, meaning 2 pi RA omega A is equal to 2 pi RB omega B. And again, all I've done is taken this and plugged these in. Okay. And you know, I told you guys the first day that if you can move things around an equation, you'll be okay algebraically. This is as intense as we get in this class algebraically. Now, later on in your engineering courses, I mean, this is in a dynamics class. Those of you going on to take an engineering dynamics class, we do this very quickly. Right? I'm going to spend 30 to 45 minutes here, and they'll spend maybe 15. And anyway. This is something we often talk about in a dynamics course. But again, it's pretty simple stuff. I'm going through it. I'm not going to expect you to do the derivations. Just understand how these equations work. And you're not even going to have to necessarily calculate anything. It's just to understand conceptually what's going on here. Notice I got 2 pi on both sides of this equation. Right, so we can say it cancels out. The mathematicians hate that. That's okay. They're non-zero. Both of these are non-zero, so they can cancel out. That's RA omega A is equal to RB omega B. Okay. So, Steve, what does that do for us? Well, what that does for us, let's say that I've got a motor very crudely drawn motor. It's going to have a shaft output on it. I'm going to draw a terrible gear. Okay? Right? A motor with a gear. We'll call this gear A. Gear A has a radius and or diameter, right? And it's going to rotate. And that rotation, if I hook that up to another gear, terribly drawn gear B, drawing quickly, I'm drawing for speed, not quality. Gear B is going to rotate this way. Now what I'm saying is I've got a certain amount of torque I'm going to get out of motor A or engine A, whatever this happens to be. Most electric motors, if you put just one battery on this, 1.5 volts, it's going to spin at one speed at one torque. If I increase the voltage, so let's say I go get a 9-volt battery and I put on this thing, it's going to spin faster. And again, voltage is how hard are you driving the electrons to flow, and the harder the electrons are driven to flow, the more torque I end up getting out of this motor, as long as I'm within range of the motor. Don't burn the motor up, okay? All right, so I can get a certain amount of torque out of this motor at A. Now, let's say I need more torque. Let's say I'm trying to pick up something heavy, and I need more torque. I can do that. There's a cost, okay? So, let's say that my goal here is to get torque into gear B. I want to apply a certain amount of torque in gear B, okay? So what I can do, so if I solve over here for torque B, that means I'm going to group my radii together. I'm going to take RB over RA times torque A. And what does that do? Well, if RB is greater than RA, notice what happens. This quantity is bigger than 1. So if I'm multiplying the torque of A by a quantity bigger than 1, I get a bigger amount of torque. Torque B is greater than torque A. I get more torque if I hook up a bigger gear to it. Okay? Well, let's look at the speeds. Let's look at speed of B. Omega B, if I solve for that, omega B then is going to be, again, put the radii together. That's RA over RB times omega A. And notice what happens here. So if the radius of B is bigger, I get more torque, but now this is the bigger quantity. This is less than 1. I'm multiplying by a quantity less than 1. Omega B is less than omega A. I can increase the torque. I can get more torque on the output at the cost of speed. The power has to be the same. First law of thermo. Energy must be conserved. I can't generate new energy in this transmission. This is a transmission. Simplest transmission. This is a transmission. I cannot generate more energy or power. Power is energy rate. I can't generate more energy I can't deliver power any differently because energy must be conserved. So the power input here has to equal the power output there. That's the first law of thermo. Technically, there's some heat lost here. That's the second law, okay? But I can't add more power. So I can get more torque at a cost of speed. So if I need to pick up something heavier, I can do that. I just can't do it as fast. Basically, is what that comes down to. Okay? I just can't do it as fast. Same thing. If I need something to move faster, well, I can do that. I can change the size of the gears relative to each other. I can put a bigger gear. I can say radius A is bigger than the radius of B. Right? So if A is the bigger quantity, then notice what happens. Now I've got a bigger quantity here. This is less than 1, so that means that the torque delivered to B is actually less than the torque supplied at A. That's okay if I've got enough torque to do what I need to do. I can just do it now faster. I can get the gear B to rotate faster than the gear A if B is smaller. So again, it's not complex. It's not really difficult algebra. More than appropriate to talk to an intro to engineering course. It's not unless you've really played with gears and stuff like that. It's not obvious. So it's worthwhile. We take a day. We talk about, hey, this is what's actually going on. If you got a motor and you're limited on what you can apply to the motor, but you want to get more out of the motor. Well, what do you want? Do you want more speed or do you want more force, more torque? Okay, and then you just adjust accordingly. Okay, now we've done for radii here. I would like to point out that, of course, the diameter of gear A, which would be 2 radii. Okay, so notice that if I take the diameter of A divided by the diameter of B, that's equal to 2 RA divided by 2 RB, which is just the ratio RA over RB. Okay? So you can use radii here. You could use diameters. I could say so it's kind of hard to, I always try to tell engineers, it's kind of hard to measure radius. It's easy to measure diameter. So diameter works just fine. I can put diameter of A divided by the diameter of B here. And that I get the same thing, right? You can see here, it's the same thing, okay? So don't try to measure the radius, just go with the diameter. Another neat tricks, professor of mine showed me one time, is, well, if you can't measure, if you don't have something handy to measure the diameter, just count the teeth. Let's say N is equal to the number of teeth. Okay, the number of teeth. Now, for these gears to actually mesh up, the space between each tooth is going to have to be the same, roughly. Okay, so the number of teeth is going to end up equaling some constant, the spacing essentially between the teeth, and then the size of the tooth that translates into a constant value. It's going to be some constant times either the radius or the diameter. Okay, so what does that mean? So that means that the number of teeth on A is going to be some constant value, which we'd have to look up or measure, times the radius of A. And the number of teeth on gear B is going to be some constant value times the radius of B. And the only way these two gears are going to mesh up is if that constant's the same. If the constant's different, the teeth spacing are different, the teeth are not going to fit together, this doesn't work. They're just going to tear each other up. But if the spacing's the same, the constant's the same, then it's okay. And so notice what happens when I put a ratio here. The number of teeth on A divided by the number of teeth on B is going to be the same constant, top and bottom, divided by the radii. So you could actually, if the gears are actually designed to mesh together and they mesh together well, then you could actually just count the number of teeth and the ratio holds, assuming they're designed to mesh together, assuming this constant's the same. Diameter always works, diameter or radius, that's always true because it's just pi, 2 pi, or no. It's 2. It's just 2, not pi. I'm getting things mixed up. But yeah, if the gears are designed to mesh together, the number of teeth also works because the number of teeth is proportional to the radius and the diameter. Questions, comments, complaints? Okay. Like I say, it's a good topic. It doesn't take real long. I'm going to stop us here. Thank you guys for joining.